Okay, so good evening, everyone. So this is going to be the last tutorial session for this NPTEL online course, and since today's is an extra tutorial session, I would mainly focus on some of the aspects that we have been trying to wind up about attitude representations and all. And so, continuing with our previous discussion in the about what we have been studying, which is Quaternions and rotation vector. So today we would be continuing our discussion on quaternions and then also talk a bit on about how to represent the rotation in terms of a single vector. So we start with quaternions. So far we have talked about what is a quaternion. That has been covered. Then the properties of quaternions. And quaternion multiplication has been covered so far. So in today's session, we'll start with how do we map a quaternion to its equivalent quaternion matrix. So this is what we are going to discuss today, right? So given that we have set two quaternions, P vector and Q vector, and we would like to find its product. The product of two quaternions, right? Of Q, P, and Q. And of course, we recall very well that this P dot Q is not equal to Q dot P, right? So let's say we start with Q dot P. So Q dot P is equal to, gives us a quaternion, of course, which is essentially the product of two quaternions Q and P vector P. And this can be written as a matrix vector product. And this matrix, say Q matrix, multiplies with this P. And of course, we recall that both the quaternions are 4 cross 1 in size. So meaning thereby that since P is a matrix of vector, which is a matrix of 4 cross 1, and then in order to be able to attain or obtain another quaternion, it should be, the output should of course be some matrix time vector gives us a vector. So it's the vector should also be of the same length 4 cross 1. So for this to happen, Q must have the size 4 cross 4. As a result, this Q is called a quaternion matrix. And this is represented as Q naught minus Q vector 1 is to 3, Q vector 1 is to 3, Q naught I3 plus C Q vector 1 is to 3. So this is the Quaternion matrix function, so to speak, right? It's a function which maps Quaternion space to R4 cross 4, right? It's 4 cross 4 matrix. And then we also can write this matrix vector matrix, this Quaternion product Q dot P. So we had talked about to be Q dot P. This can also be written as a pre-multiplication of Q conjugate P dot Q. It can also be written like this. Now, this Q here, Q bar, is called conjugate Quaternion matrix. And it's given by, the mapping is given by Q bar is H is mapped to R4 cross 4. And its representation would be Q bar as a function of say any Q is equal to Q naught minus Q1, minus Q 1:3 transpose, and it would be Q vector 1:3, and it would be Q naught I3, which is identity matrix of order 3, minus C of Q vector 1:3. So this is what, so we notice the sign distinction, sign difference between. So the Quaternion matrix is written as Q naught minus Q vector 1:3 transpose Q vector 1:3 Q naught you see the note the sign difference here, this and this. So that is how they are distinct, right? And its representation in 4 cross 4 would be, so let me expand it here. So this can be written as Q naught minus Q1 minus Q2 minus Q3, then Q1, Q2, Q3, and then of course Q naught is identity, Q naught, and then the skew matrix, or what we call cross product matrix of where Q is Q vector 1:3 is a vector. So the its corresponding skew symmetric matrix would be given by minus, it would be Q3 minus Q2, and of course Q1, then we'll have minus Q3, Q2, this would be Q2, and this will be minus Q1. So this is what it is, right? And likewise for Q conjugate, let me write it down here. Try again. Okay, so let me try to Since it's not working, let's do it here itself. So it will be Q naught and then Q1, Q2, Q3. And here we have minus Q1, minus Q2, minus Q3, right? And then we have Q naught, Q naught, Q naught. Then we have minus Q3, minus Q plus Q2, minus Q1. Then likewise Q3, minus Q2, Q1. So these are our, so to speak, the matrices, equivalent matrices, right? Now there are certain properties from here that we can deduce. So this is equal to Q of Q vector transpose. So there are certain properties. So we have Q of, for any generic, I think there was some mistake here. Yeah. So it should be that Q of Q vector, Q conjugate vector is equal to Q of Q vector transpose. There is one such rule, and the other such identity is Q transpose Q conjugate of Q conjugate of small q is equal to conjugate of capital Q small q transpose. So these are the identities. Fine. So now also let's talk about the derivatives. So far, say given we had q vector dot p vector is equal to qm. Then arguments as q vector comma p vector. So this was our one such multiplication, and this could be written as q of q vector dot p is equal to q of q conjugate of p vector dot q vector, right? So therefore, the derivatives are partial of q vector m p vector divided by is equal to. So this, if we are differentiating with respect to small q, then this would be q conjugate of p. And the second one, say when you're differentiating qm with respect to p, so this would be given as q of small q, right? And likewise, we can also perform the derivatives such as partial capital Q by partial Q naught. This would be something which can easily be done. Likewise, Q1. Right? So let's just try to do for Q naught. So where all we do we see Q naught? So Q naught appears here. In all case, what we observe is Q naught always appears in the diagonal. So because of which, when we differentiate with respect to Q naught, it will be an identity matrix of order 4. So this is what we get. And likewise, it can be repeated for others as well, right? Now let's talk about unit quaternion. Let's just use a different color. Unit quaternion to rotation matrix. As we recall, quaternions, the unit quaternions are essentially quaternions whose norm is 1. And mind you that they can be used to represent the attitude of a rigid body. Right? Now uh, say we have a vector. Say we have a vector Z is an element of R3 space in the global coordinates, global or the world coordinates. And if Z prime is an element also an element of R3, is the same vector, if it's the same vector in the body fixed coordinates, then we can have the following relations. It is 0 Z vector prime is equal to Q vector dot 0 Z and Q inverse. And of course, as we recall, the inverse of a quaternion is its conjugate. So this would be written as Q dot 0 Z dot conjugate. Now what is to be noticed here is that why we to add 0 here. So the 0 is added for compatibility, just for compatibility requirements in during matrix vector operations, matrix vector multiplication operations. During, yeah, just for this. For so this part, this we can also write it as Q conjugate and Q transpose Okay, so yeah, this we can write it as follows. So we can write Q conjugate Q transpose into Q of Q into 0 Z, right? And then we could also in some sort of a combined matrix vector product, we could write this as 1 0 transpose, and mind you that 0 is a vector here, And then we have, of course, zero vector, and then RQ as a function of Q vector, 0, Z. And here this RQ is not, it can just an abbreviated form of Q transpose into Q. So that's how we do. And we can clearly see from here that the Z prime is equal to RQ of Q vector into Q into Z vector. And likewise, Z is equal to RQ of Q whole transpose into Z prime, right? And one thing to be noted is that the sequence of rotations are represented by products of quaternions, right? And which leads us to say that RQ of Q dot P is equal to RQ of course Q, then you have RQ of P vector, right? And then RQ, these are just the, when you apply rotations uh, on a product of quaternions, this is equivalent to rotating the quaternions initially and then multiplying them, right? So now let's just come to quaternion rates to angular velocity. Now here what happens that the time derivative of the unit quaternion is the vector of quaternion rates. And so the quaternion rates are related to the angular. This makes that quaternion rates are related. There is some relation between the quaternion rates and the angular velocity. So the function that map a unit quaternion and its temporal derivative to the angular velocity are given by WQ, right? So what they do is, so WQ is a function that maps a unit quaternion and its temporal derivative to the angular velocity in say world coordinates, right? And for body coordinates, the function that we have is WQ prime. And how do they relate? So that we do by, we first construct, say, WQ is the mapping which maps from H cross R4 to R3. So it takes into so we have so we have WQ is a mapping from H cross R4 to R3. So here H indicates that Q is an element of H. R, this indicates R4 is the space in which we have the Quaternion rates, and R3 is the angular velocity W. So the way we do is the mapping goes as 0 WQ. It takes Q and Q dot as inputs, and this is equal to Q bar dot Q dot is equal to Q right. And for the WQ in or for body fixed coordinate system, we have zero WQ prime, Q and Q dot. This is equal to Q dot Q conjugate. So this is equal to Q conjugate of Q vector transpose into Q dot. Right. So this is what we do here. Now, this from here we could write, say, just the WQ. So WQ is equal to, as a function of course, Q and Q dot. This is equal to 2 of capital W into Q vector into Q dot. And this one could also be written as, so here this W is a matrix of the size 3 cross 4. So in fact, W is a mapping from H Quaternion space to R 3 cross 4 matrices, right? Space, so to speak. In this case, now we have that Q dot is equal to 2 into, and this will also be conjugate of, not conjugate, the representation of W in, so to speak, in the body fixed coordinate systems, then Q dot, right? And this is also function which maps from the Hamiltonian space, or the in this case here we have in the Quaternion space to a matrix of size 3 cross 4. Right? So now what we do is, So this is what, and then we could also discuss about the how to obtain quaternion rates from angular velocity. So here the inverse mapping from the angular velocity and the unit quaternion to the quaternion rates. So this is what we are talking about. So in this case, say we have a q dot omega, which is just a way of saying that we want to find the rate of quaternion rates corresponding to an angular velocity omega. Now in this case, you have from h cross r3, it maps to h indicates quaternions, and this is an element of q. This is this is the space consisting of the angular velocity w, and we want it to map to quaternion rates, right? So this could be written as q dot omega is a function of q dot comma omega vector. Sorry. Now this is equal to half of q dot 0 omega, and omega is a vector here. So this we could write as the matrix vector product, right? So the corresponding uh, quaternion matrix dot 0 omega. Omega is a vector here. Now for omega prime, which is just the representation of, say, in which case we are dealing with body fixed coordinate system. In this case, we have half of q half of 0 omega vector prime, which is the angular velocity in the body fixed coordinate system, time q vector. This would be equal to half of q transpose, q conjugate into, right? So this is what we are. And in a simplified version, we could also have written this as, since anyway we are not when we do a matrix vector product, so the first row here will multiply with the, no, sorry, every element of the first column of q would be multiplied with the first element of the vector. However, the thing is, first element of the vector is 0, so it doesn't matter if we have the first column or not. So that's the reason for a, say, in a more compact fashion, we can write this as half of w as a function of q transpose. Now w of q was a matrix of R3 cross 4, and its transpose is 4 cross 3. So which means that three columns are compatible with the three elements in the angular velocity vector. And likewise, this could also be written as half of uh, W conjugate, or sorry, W in the represented in the body field coordinate system, Q transpose omega prime, right? So this is what it is. Now let's talk about rotation vector. So what we have is the rotation vector representation. So one, so to speak, a demerit of quaternion is that we need to we need it to have a unity constraint. And for this to happen, we require that it should be expressible in the form of that its norm squared should be equal to 1, right? That's how we obtain its. So this is the, so what we see here is that this is a quadratic, we call it quadratic norm constraint. And so it must have this this quadratic norm constraint so as to be able to be considered as a valid rotation. However, the thing is, we can still overcome. This can be overcome by folding the unity norm. It's called the unity norm constraint into the parameterization. Right? But there are several ways in which to do it. Of course, like in order to have such quadratic norm constraint, you can do in an infinite number of ways. But one thing which is one of which is very useful, which comes in handy, is what we call as the 3D three-dimensional parameterization of the quaternion. So 3D parameterization of the quaternion. Quaternion representation of the or of an object's attitude. Right? So let's first start with what is the rotation vector? Right? What was an axis angle? So now the rotation vector is a function of axis and angle of a rotation. Which is VA vector R cross S2 2 or 3 and by VA this is what it is, rotation vector. It's a function of axis as well as the angle of a rotation. So here R here indicates this R is a number or a scalar. Is a scalar. Scalar is angle in this case, and S2 is a vector which whose tips or whose tip lies on the boundary of or on the surface of a sphere. So it's like take a sphere, center it at the origin, and draw a vector with its tail at the origin and head on the surface. So surface S, right? I'll call this surface so as to not lead to new conventional conflicts, convention conflicts. So here what we have is, so, and this sphere has a radius 1, r is equal to 1. So this vector, right? This vector, it's a vector here. Although it lies in 3D space. So in this case, say vector, this one, we have v1, v2, v3 are the components of this vector v. Although they lie in 3D space, however, they only have, they seem to have 3 components, but one of the components is like redundant. It's like if we know 2, the third is easily known. Why? Because the norm of this vector is equal to 1. And because of which it has only 2 degrees of freedom. And this we call it as v vector is an element of S2. So it's like, so S2 represent a sphere of third dimension. So the convention is like S into n minus 1, S to the power n minus. N is the number of dimensions. So number of dimensions. This is because there is a constant which forces any element belonging to this say space or set, because of which it's not all the components of that member are independent, right? They are bound by a certain constant. In this case, it happens to be that the radius or the norm of vector has to be 1, right? So is vector, this indicates our axis of rotation. Fine. And this was our that v vector is the rotation vector which takes 2 parameters, alpha and n vector, and this is defined as alpha into n. Alpha is the angle of rotation and n is the, so this alpha is the angle and n is the angle of axis of rotation. Now, so this was like angle axis, right? Angle axis. How do we go the other way? So say given that you have axis and angle, or given that you have rotation vector, how do we move to axis angle? So in this case, what we know from beforehand is that the norm of the axis of rotation was axis vector is 1. And this makes at least one thing clear, that our n vector associated with v vector is defined as just the, so rotation vector was v vector. So v vector divided by the norm of v, this is equal to our axis of rotation. And we could write as v vector divided by small v. This indicate this small v is the norm of v. And likewise, the angle can be extracted as defined as just the norm of v. This could be small. So this is what it is. Right? Now let's talk about how are the rotation vectors related to the unit quaternion. So in this case, we are looking at, say, quaternion, which of course takes maps R3 to the H space. Now Q vector is defined, we'll take this rotation vector as an argument, and this is equal to QA, which is associated with the rotation by this V, by this angle of rotation, which is of course a function of V vector, and then axis of rotation, of course, a function of V vector. And this could be in shorthand notated. I mean, this is represented explicitly as cos of V by 2, and then V vector by small v into sine of V by 2. So this is what it is. And so this is the most popular, you'll find the representation of a quaternion in robotics mostly. So this representation is very common. It's very widely used in any way where it involves attitude dynamics. Fine. So we can go the other way around. Now say we know the we know the quaternion, right? So we are looking at the inverse mapping now. So the idea is, given any rotation vector, or maybe I should write as given a unit quaternion, what is its corresponding rotation vector? So that is the question we are asking ourselves. So we are looking at the inverse mapping, which maps V vector from H space to R3. And this is given as V vector is defined as alpha q right? So alpha q as a function of q vector, then n q vector. Now what we recall is, so look at the first here, the first element of this vector. So cos of V by 2. So it was like we were looking at cos of V, norm of V, as we recall, was also it's also the angle as an angle of rotation, right? So cos of alpha by 2, this is equal to q naught, isn't it? Just by equating we are equating these two things. So cos alpha by 2, and then V vector by V into this is the unit vector associated with the rotation vector V into sine of alpha by 2. And this has to be mapped to q naught q vector 1:3, right? So balancing the corresponding components, right? So cos of alpha by 2 is equal to q naught. This we can write as alpha by 2 is equal to cos inverse of q naught, and which makes that therefore alpha of q as a function of q vector, this is equal to 2 into cosine inverse of q naught, right? Now for the axis, what we do is, n vector associated with q vector, this is equal to q vector 1:3 divided by norm of q vector 1:3. That's how we are able to clearly obtain, right? So this was, I think, with this we are able to complete what we had intended for quaternions and rotation vectors. So now I would just like to discuss whatever was taught in little bit about what was taught in the week 8 of this course. So week 8, what was taught in week 8, right? So in week 8, we were discussing about how how do we, or what is the relation between the work done by the on the input side to what was the work obtained on the output side, isn't it? So this helps us to be able to, so the goal is to determine actuator, or maybe input driving force to the actuator, and so that's what we are aiming at, right? So this will eventually drive the load at output. Ultimately, eventually we use mechanisms for what we call as the force transformations, right? So mechanisms are meant for force transformation. So we provide certain force as the input, we look at, and we use it to be able to drive some load at the output end, right? So this makes us, that's the reason we do this, what we call as the, so this falls under force analysis. So this helps us to estimate the amount of load we would require to input to be able to do some certain task, right? That is the whole purpose of the work of the force analysis problem. Now, in this case, we will be doing, of course, in this case, here we are doing a quasi-static analysis. Quasi-static analysis. To obtain, so the goal is to estimate the actuator forces, torques, right? And we perform a quasi-static analysis, assuming, so the first assumption is that there is no energy loss. So the system is ideal. Mechanism is an ideal system. So what we do is we use the principle of virtual work. So the idea is that we look at all the work done, right? So the idea is that so the work done by all the forces, so this is external force, and this is some virtual displacement. Right. So the idea is that the work done by all the external forces for a system in static equilibrium, work done by all the forces, all the external forces is zero. So that's what the essential goal here is to. And this drives, uh, like this virtual order principle is widely used in mechanics to be able to determine the equilibrium equations as well, and to be able to obtain at first the governing equations to many a problem. And in such problems like the ones we are dealing with, it will help us to estimate to get a relationship between the input load and the output load, right? And of course, this should be valid for all or any virtual displacements, which are consistent with the constraints. Now, what are virtual displacements? Sorry, I think I hope it's saved since the last time we opened. Constants and the constraints. Now, what we are looking at, what are virtual displacements? So these are imagined displacement with time frozen. So it's as if you have a body and say this body is under equilibrium, right? There is a floor, you're applying some force, an equivalent amount of force is being acted on the body by the floor. There's something what we call as normal force. And say we are applying some force here, say G, and then you have, and the force is less than that of the friction force, right? Or maybe say equal to that of the friction force, but less than the critical, I mean, the critical friction that is required to overcome the static friction, right? So we are applying, say, G, which is less than mu into F, mu into N. So what happened is, say this system is right now under static equilibrium. However, say you allowed it to slightly displace. I think the colors are not distinct. Let me use a different color. So we allow it to slightly displace. And this displacement is delta. What and this is, mind you, this is virtual because the displacement is not taking place in reality. We are just allowing the system to what? To undergo some displacement, which are consistent with the constraints. The constraint is that this displacement can only happen horizontally. The reason why? Because this floor here prevents it from having a displacement vertically. And also because of the force that we are applying a compressive, I mean, say a force which is meant to keep the body, this body B, in sticking to the floor, right? So providing this virtual displacement, what we will have is the net amount of force that is acting here is, say, force, or sorry, not the work done by, mind you, the displacement is taking this direction, right? This direction, and G was acting along. So say we have this X direction, this is our Y direction. So G is acting along positive X direction, and F is acting along this small f, which is the frictional force, is acting in along the negative x-axis, right? And the displace and this virtual displacement is also taking place along the positive x direction. So what happens is the work done by G is equal to, so force and displacement are in the same direction. So we will have say we call it WG, and I'll not call it WG because it's not real work. So I'll just call delta WG, which means that it's some imaginary work done. This is equal to F into delta. Now work done by small f. So this will be equal to delta small f. But in this case, force and the virtual displacement are say aligned along two different aligned along opposite directions, right? So because of which we have delta wf to be minus of, sorry, this would be g here, minus of small f into delta. And from the principle of virtual work, summation of, or what let me, since we have a small system, we'll have w delta wg plus delta wf is equal to 0, right? From the principle, this is from virtual work principle. And this implies that we'll have g into delta minus f into delta is equal to 0. And this implies that g minus f into delta is equal to 0. And we recall that since delta is not equal to 0, because we are providing some finite, but although it's imaginary, but it's still non-zero displacements, this implies that g minus f is equal to 0. And this implies that g is equal to f. And as you recall clearly, this is what we would have obtained from equilibrium condition. This we can do very easily, right? So say summation of force along x direction is equal to g, which is acting along positive x direction, minus f is equal to 0, right? And this implies d is equal to 0. So see how clearly we are able to get the work. So the claim equation from the virtual work principle, right? So this is what we eventually do in principle of virtual work. No matter how complicated the situation is, all that we require is that our work, sorry, the virtual displacement must be consistent with the constraints on the system. In this case, this block was only able to move horizontally along the table, and that we have to respect even when we provide the virtual displacement. And what is being assumed is that this entire virtual displacement was done, this was given for 0 time. It's as if it's as if even if the body was moving, time still remained constant. So that is what it is, right? So we just freeze the time, and then we provide this virtual displacement. Of course, since this motion is not taking place in reality, there has to be, the imaginary situation is that everything is happening as if the time has frozen. And of course, there is a concept which you may have, if in certain movies you will have seen such scenes, right? That uh, the protagonist will just move around and he will just freeze the time, and it's something like that. Just imagine, just use that scenario to understand the situation. And I believe with this, I will be closing it for today, and I think for the course. So the course ends here, and my sessions as well. For any further information, and if you would wish to contact me, then my contact details are my safe at first webs. I'll just give my email. So my email is Krishna A G R at iisc dot ac dot. So this is my email ID, and of course my LinkedIn ID is linkedin.com/in or maybe just leave it /KC author, you can say. And of course, yeah, a lot of communication can be done through LinkedIn nowadays. So yeah, so these are the two ways of reaching out to me. Contact. Yeah, and I believe I'll just end today's session. It was nice interacting with whomever it was possible for me to. Okay, so bye and best of luck for the exam. Yeah, you have any question? Hello. So do you have any question? I think it's Archana, right? Okay, since okay, then I'll just close the session for today. Bye.